welcome everyone. If you would like to be added to the mailing list of the seminar, please shoot me an email. My email is florencia.oros@colorado.edu. And thank you so much, Andy, for speaking today. Andy will be talking on trialities of W-algebras.
Shall I get started?
Yeah, I think so.
Okay, so it looks like there's some other people that weren't here for Thomas's talk, which is unfortunate because I'm basically picking up where he left off, or at least in a certain direction of where he left off. So what I'll do is I'll assume that people know definitions of vertex algebras, and I'll just introduce some notation for the examples that we need. And what I want to do today is state precisely the triality result in type A that Thomas was alluding to. He didn't state the whole thing, but he looked at some cases of it. So I'm going to state the general case in such a way that motivates a similar statement for types B, C, and D, which is more complicated. And I'll state that later, and I'll say a few words about how these things are proven and maybe some applications depending on how long we have. Let's see. Okay. So first, let me just mention some examples of VOAs, the ones that we'll need, and fixed notations. So first of all, the universal affine vertex algebra, VKG. So G is supposed to be a finite dimensional, simple Lie superalgebra. Maybe Lie algebra, maybe superalgebra. K is the level. And this is a structure that is acquired by the vacuum module over the corresponding Kac-Moody Lie algebra or Lie superalgebra. So V upper K always denotes the universal affine algebra or the vacuum module. And then I can consider its simple quotient, which I'll denote by L lower KG. Okay, this is irreducible as a module over G hat. Generically, they're the same thing, but for special values, they're not. The W algebra that I can associate to G and nilpotent, the nilpotent for this talk will always be an even nilpotent. I'll denote by WKGF, and K is also the level, and W lower KG will be the simple quotient. Okay, so if F is principal nilpotent, then I'll drop the F and I'll just write WKG. That always means principal W algebra. So one of the symmetries that the principal W algebras have is the so-called Fagan-Frankel duality, which is that as a one-parameter vertex algebra, WKG is isomorphic to the W algebra of the Langlands dual Lie algebra with a different level K prime. And they're related in this nice way, where the R check is the lacing number of G, and then R check times K plus H check times K prime plus the other LH prime is 1. Okay, so for this reason, it's often a good idea to replace the level with the shifted level. It's K plus H check. So usually I'll do that. Sometimes I'll change notation a little bit. So I want to mention one more thing, which is coset construction. So this is a general construction in VOA theory for constructing new vertex algebras from old ones. And it's analogous to the coset construction in say, associative algebras. So if V is a vertex algebra and A is a subalgebra, the coset, which I'll denote by com-AV, or also called the commuton, is simply the subalgebra of V, consisting of elements that commute formally with everything in A. Okay, so as power series, they commute on the nodes. It's the same thing as having trivial OPE with everything in A. And it's easy to see that this is a vertex subalgebra. And in particular, if V and A have, say, Virasoro elements, LV and LA, then the difference between these, LV minus LA, is a Virasoro element for the coset vertex algebra, and A tensored its coset embeds conformally in V. Okay, we also can say that V is a vertex algebra extension of A tensor sig. So I want to mention a recent result, which is coset realization of certain W algebras, and then try to put this theorem in a more general context later in this talk. So it was shown a couple of years ago that if G is simple and simply laced, then there's a nice coset realization of its principal W algebra. So first of all, when I say coset realization, that means that we can realize this algebra as a coset, in fact, as a one-parameter family of algebras. So I take the affine vertex algebra G at level K, and then I tensor it with the simple level 1 affine vertex algebra. And there's a diagonal embedding that takes the generators of VK plus 1G to the sum of the two. So I write XU tensor 1 plus 1 tensor XU. This gives a diagonal embedding of the level k+1 affine algebra, and then CKG is the coset of the image of this map in this tensor product. And it's the same thing as taking the invariance under the Lie algebra G of T, which is sort of half of the affine Lie algebra. So this turns out to be isomorphic to the principal W algebra G for all ADE types with a particular level shift. Okay, so before I say anything specific, let me just give an overview of what I mean by trialities of W-algebras. So sort of in a general setting, let's say that I have a Lie algebra or Lie superalgebra G. I have a nilpotent element F. This F I can always complete to a copy of SL2. And it may have a centralizer that's non-trivial. Let's say A is the centralizer of this SL2 in G. The corresponding affine W algebra with this nilpotent has affine sub-VOA of type A. It's got, and there's some level L that one can calculate. There's an affine subalgebra VLA. And when I say the affine coset, what I mean is take the coset of this affine subalgebra inside this W algebra. Okay, and sometimes I actually have to modify this a little bit. Sometimes in addition to taking this affine coset, I have to also take the invariance under some outer automorphism group. So if I do that, I'll mention it, but that will always be soaked up into this notation. So CKGF either denotes the honest affine coset or maybe with some additional invariance under an outer automorphism group. And so trialities are not actually isomorphisms between W algebras themselves, but they're isomorphisms between the corresponding affine cosets. And triality means that there are three different affine cosets that are isomorphic. And so typically these are different Lie algebras, different nilpotents. Sometimes one's a Lie algebra, one's a Lie superalgebra. And these are isomorphisms of one parameter families. Okay? And they can be thought of as, well, they generalize various known results, including Fig and Frankel duality, the one that I mentioned before. In this case, these are principal W algebras, so there is no affine subalgebra, and affine coset, just you don't do anything, it's just a W algebra. But typically, you have to take this coset. So in one direction, it generalizes Fig and Frankel duality. That can be seen as a special case of one of these isomorphisms. Also, this coset realization that I mentioned in type A, and as we'll see also in types B, C, D, and some other types. There are such coset realizations that also belong in this picture. And also some of the dualities that Thomas mentioned in his talk last time, these Fig and Sinikatov dualities also are part of this picture. And then there's many new ones as well that weren't previously written down. Okay. So the ones that I'll start with are the ones that Thomas mentioned last time. So this is a little bit of a repetition of what he said, but I want to set this up as a way to motivate the story for the other types. So these W algebras, as Thomas did, I'm going to call hook type, or he, I guess, called them small hook type W algebras. So let's say that, well, first of all, the nilpotents in SLN correspond to partitions of N. And I'm going to set this big N to be little n plus m. And for the moment, I'm going to take little n to be greater or equal to 1, but later there will be some extreme cases that I'll define differently when n equals 0. For the moment, little n is greater or equal to 1. And I want to think of SL n plus m as decomposing in the following way. So first of all, there are two Lie subalgebras. There's an SLN. Well, I guess if n is 0, that's nothing. That's just there's nothing there. But if n is greater than or equal to 2, there's an SLN. And there is a GLM. And then the rest of it decomposes as a sum of two modules for SLN plus GLM. One of them is standard for SLN and conjugates of the standard for GLM, and then the other way around. So you can decompose SLN plus M in this way. And then the nilpotent that I want to consider is the one which is principal in SLN and trivial in GLM. So you think of it as the sum of two nilpotents with these properties. And this corresponds in this language of partitions to the hook type partition where I have one big block of size n. This is the block where this is principal, and then the rest of them are small blocks, just a bunch of ones. Okay, the shifted level phi is k plus n plus m. And I'm going to sort of introduce simpler notation. W psi of nm means exactly the W algebra of this Lie algebra SLN plus M with this nilpotent. And here I'm using psi to be the shifted level. So that's the same as W psi minus n minus m using the usual level. Okay, that's my hook type W algebra in type A. And as Thomas mentioned before, this generalizes some known examples. So if m is 0, this is the block where the nilpotent was trivial, then I just get the usual principal W algebra. If m is 1, then I get the subregular W algebra. If n is 1, then there's no block in which this thing is, the nilpotent is principal. It's just a trivial nilpotent. So W psi 1m is just an affine Lie algebra. That's the same as a W algebra with a trivial nilpotent. And if n equals 2, it's sort of one step worse than the affine algebra. It's the minimal W algebra. This becomes the minimal nilpotent. Okay, so these are some cases that are familiar that this unifies. So let me say a few words about the structure of this W algebra. It's got an affine subalgebra of type GLM, which I think of, sometimes it's convenient to think of it as Heisenberg tensor affine algebra of SLN. It has additional even generators in weights 2, 3, up to n. So one additional field in these weights, which are invariant under the affine Lie algebra GLM. And then it has 2m additional fields in this weight n plus 1 over 2. And as a representation of GLM, it transforms as the standard representation plus its dual. Okay, so that's the structure. It's freely generated by fields of this kind. And then I said before that when n is 0, we have to define things differently. So I can define a similar structure with the same generating type and similar properties, and I can deal with it in the same way, but it's not actually a quantum Hamiltonian reduction. So the way to define it is that if m is greater than or equal to 2, the 0m algebra is just this affine algebra of SLN tensored with a beta gamma system of rank m. When m is 0, when n rather is 0 and m is 1, I just have the beta gamma system. You can think of it as this affine piece is just 0, is nothing, just the complex numbers. And then when they're both 0, I define it to be just the complex numbers. Okay, so those are some extremal cases. That's all I want to say about these hook type W algebras. I'm going to come back to that in a minute, but I also want to define a family of super W algebras, which I'll also call hook type. So they're very similar, except that now instead of taking SLN plus m, I take the Lie superalgebra SLN/m. And I want to decompose it in a similar way as SLN plus GLM plus some modules. These modules are the same as the ones before, except that they're now odd field because they live in the odd part of this Lie superalgebra. And the nilpotent that I want to take, I'll use this notation. It's simply the one which is principal in SLN and trivial in GLM. So it's very similar to the other picture. My shifted level looks a little bit different now. And now I'll call these W algebras V psi and m rather than W psi and m. It's just the W superalgebra with this nilpotent. And there's one little wrinkle in this super case, which is that when n equals m, I have to do things a little bit differently because I want my W algebra to be simple. So instead of taking SLN/n, I replace it with PSLN/n, and then I get simple algebra. And again, these unify some algebras that are well known. So there's, when n is 0, it's the same as before. I just get the principal W algebra of SLN. When m is 1, then I get the principal W superalgebra of SLN/1. And when n is 1, then I just get an affine Lie superalgebra. And sometimes it's convenient to shift. So in my previous notation, this would be associated to SL1/m, but I think my notation, I think I wrote this wrong. This should be, I should switch this with SLM/1. Anyway, it's, no, I guess this is, I think I switched my signs here. So in this case, I have a Lie superalgebra, and then in this case, I have a minimal W superalgebra. So again, these are some familiar special cases. And again, I should tell you something about the structure of these W algebras. So first of all, they have an affine subalgebra of type GLM, when m is not equal to n, or SLN when they're equal. There are additional even generators in weights 2, 3, up through n, which are invariant under the affine subalgebra. And then there are, in weight n plus 1 over 2, there are, again, 2m fields that transform under GLM as the standard representation plus the dual. The only difference is that these 2m fields are odd because they correspond to odd elements of the Lie superalgebra. So it's a very similar structure to the previous case, except that these extra fields are odd. And then as I said before, in the other case, there's some, when n is 0, I have to define things differently. So just like before, when n is 0, if n is bigger than or equal to 2, I just have an affine Lie algebra tensor now with a BC system rather than a beta gamma system. The 1-1 case, I have a symplectic fermion algebra. 0-1 case, I have a rank 1 BC system. And then these two cases, 0-0 and 1-0, turn out to be the complex numbers. The reason for these extremal cases is so that the general result that I state holds for all m and n. Okay, and also that the proof can be done in a uniform way. Okay, so now we have our algebras, our W-algebras that are of interest in this situation. So now I can state the triality result. So I have to introduce the affine cosets. So in the case of the hook-type algebras of type A, I don't have to take any orbifold by some group. I simply take the honest affine coset. So this C psi NM is just the coset of WKNM. That was the one for the Lie algebra, not the Lie superalgebra. When n is not equal to m, I have the same thing for the Lie superalgebra, for the W superalgebra. I just take its affine coset. And when n equals m, now my affine algebra is an SLN, but I want to be taking invariance under GLM together with the affine part. So I have to also take a U1 orbifold of this. So there's an action of U1 by outer automorphisms that survives, and I have to take the U1 orbifold. And I'm going to continue calling it D psi NN. Okay, so these are the objects, and the general duality theorem is that for all n and m, here I've written it so n is greater than or equal to m, I have these three isomorphisms as one parameter families. So there's a D algebra is isomorphic to a C algebra, which is also isomorphic to a D algebra. Okay, and these two levels, or shifted levels, psi and xi prime, are related in this very nice way. So this was conjectured originally in physics by Gayotto and Rabchak. And as Thomas mentioned last time, this part I won't repeat. This is a common generalization of several statements, including Fagan-Frankel duality in type A and the coset realization of principal W algebras of type A, and also some statements that were conjectured by Fagan-Semikato that have been recently proved by Genra, Nakatsuka, and Thomas in a different way. Okay, so any questions? Because I'm sharing screen, I can't see anybody's faces, so I have no idea what sort of reaction I'm getting. But if I have the pictures, then I can't see my slides. But this is sort of where Thomas left off. So are there any questions before I continue? What I want to do next is say a few words about the proof of this very general statement, and then use this picture to define state the analog in B, C, and D types. Okay? So no questions, then I'll continue with that. So the main object that is needed to prove this, at least in the way that we did, is the universal two-parameter W infinity algebra. So this is an algebra that was expected to exist for quite a long time, starting in the early 90s. So there were some papers that mentioned it and gave a fairly convincing, a lot of evidence for its existence and uniqueness. It was not mentioned so much in the literature for a while, but became interesting again around 2011 in some work of Gabardine and Gopakumar. It's relevant for ADS-CFT correspondence. So they also did some similar calculations to the ones in this very old paper of Yu and Wu. It gave very strong evidence for its existence and uniqueness. And this is something which I wrote a paper about a few years ago, the existence and uniqueness of this structure. So my notation is a little bit different. There are some reasons why I choose different parameters, but it's up to change of variables, the same structure. So the statement is that there exists a unique two-parameter W infinity algebra. So two parameters means that it is defined over a ring in two parameters. And my choice makes this a polynomial ring. My parameters are central charge C and some other parameter lambda. So saying that it's of type W, 2, 3, et cetera, means that it's got one strong generator in weights 2, 3, 4 all the way out. So it has infinitely many. It's a very large object. It has a Virasoro field, that's the weight 2 field of central charge C. It's got a weight 3 primary field W3, which is normalized in this way, which is sort of convention, but there's no particular reason to do that. And then these higher fields, W4, W5, W6, are all defined recursively as descendants by this action of W3 first mode. This is a mode that raises the weight by 1. So the higher ones are no longer primary, but it's convenient to define them this way. And then the resulting algebra, well, it's generated by the weight 3 field, but it's not strongly generated. It's strongly and in fact freely generated by all these fields, which means that it admits a PBW basis that consists of all the normally ordered monomials of these things and their derivatives. And if you consider its OPE algebra, there are nonlinear terms, but the structure constants are all polynomials in C and lambda. So that's what I say when I say it's defined. That's what I mean when I say it's defined over a polynomial ring in two variables. And you can think of this as a kind of classifying object for VOAs with certain strong generating type. So all VOAs of type W2, 3 up to n for some n, satisfying some very reasonable hypotheses that are easy to check. They're all quotients of this algebra. So for example, W-algebras of type A, principal W-algebras of type A are quotients of this algebra. And this is a two-parameter algebra, so those are one-parameter quotients. There are many other structures as well that are one-parameter quotients of this algebra. Okay, so some other features of it. So I mentioned that it's defined over the ring of polynomials in two variables. So it's sort of, you can think of it as being of CFT type in the sense that the weight 0 piece is exactly this ring. Usually we work with VOAs that are defined over the complex numbers, and weight 0 is one-dimensional. So here weight 0 is a rank 1 free module over the ring. Now, if I consider ideals in the polynomial ring, let's say prime ideals in the polynomial ring that are generated by just one polynomial, these variables, I can consider the VOA ideal generated by this weight. I can think of this I, which lives in the ring, as sitting in the weight 0 subspace, and then let it generate a VOA ideal, which is just the set of I linear combinations of things in my VOA. And I can take the quotient, which I'm going to call W upper I. It's just the quotient of WC lambda mod I WC lambda. So this is a VOA that's now defined over this quotient ring. It has the same graded character, and the structure constants are just the reductions mod I of the original structure constants. But I can take this VOA over I can mod out by this I. And why is this interesting? Well, in an appropriate sense, this big VOA is simple. And if I pick a random ideal, this will still be simple. Simple here means that it's not the same as admitting no non-trivial ideals, but every non-trivial ideal intersects the weight 0 piece. That's what it means to be simple in the sense of VOAs over rings. So generically, these are simple, but if there's certain special ideals where this is not simple, what does that mean? It means that it admits a non-trivial graded VOA ideal that doesn't intersect the weight 0 piece, or it only intersects it in 0. So if I have such an ideal, then I can take the simple graded quotient. I'm going to denote that by W lower I C lambda. So all interesting one-parameter quotients of this vertex algebra arise in this way. And it becomes an interesting question to classify all the I's where this has a degeneration. So this is still actually an open problem, but there's a conjectured list of all such ideals. And all the ones that are expected to arise actually do, and that's one of the things that we prove. But we still don't know that this is the complete list. And moreover, the ones that arise in this way are exactly these things I mentioned a minute ago, these C, psi, NN, and D psi, NN. Okay? So anyway, so we need this object, we need to consider its one-parameter quotients. So the way that we deal with the triality problem is that these affine cosets that I mentioned before, I want to first understand their generating type and show that they are on the list of one-parameter quotients of this W infinity algebra. So to get a handle on their structure, I have to pass to the large phi limit in an appropriate way where I scale the generators correctly. If I do this, then in the limit, these cosets are generally harder to analyze than orbifolds. Orbifolds are just invariants under a group, but they turn into orbifolds of generalized free field algebras, which are like free field algebras in the sense that only the vacuum appears in the OPEs, but it appears at different heights. So these turn into orbifolds of generalized free field algebras, which then can be analyzed using classical invariant theory. And it turns out that that they have, at least in the limit, they have generating type W23 up to some t, which is determined from invariant theory. And moreover, the generating type of the limit is the same as the generating type of these one parameter algebras, which is, that kind of statement is true in a very general setting. So we get that these algebras, these affine cosets, are of this generating type. And then, as I said, the two parameter W infinity algebra is a classifying algebra for such structures. So we get that these actually are of the form Wi C lambda for some ideal I. There's a little bit of work to do to prove that these are the simple quotients, but it's not so difficult. So we get that these are object of this form. So the question is, how do we determine what I is using the data that define these W-algebras and their affine cosets? So we can think of the original W-algebras, this is the even one and this is the W superalgebra, as VOA extensions of the affine subalgebra tensored with this W infinity quotient. And we know something about the extension. It's generated by two n fields, which are either even or odd, depending on whether I'm working with this one or this one, in a particular weight with a particular transformation under GLM. So it turns out that data is enough to uniquely and explicitly determine this ideal I. So how do you do this? You work with the OPE algebra of the universal structure, and you leave the other parameter, this parameter lambda, undetermined. And then by applying certain VOA identities, it doesn't take very long to determine what this lambda must be. And it happens uniformly in all these problems at fairly low weight. So we actually get a formula for I in the sense that we parameterize the corresponding variety using this level psi as a parameter. We get the equations for these I's, and then all the trialities that I mentioned are simply consequences of symmetries of our formulas. So the key step is to compute these I's, then you get these triality statements for free. Okay, so that's a sketch of the proof. Any questions about that before I move on to BCD types? I should have a quick look and see if everyone's still paying attention. So far, so good? Okay, so let me use this picture to motivate the BCD type. So this is, of course, more difficult, but the way that we frame this is that it's sort of natural to at least identify candidates. So there are going to be 8 families of W algebras and W superalgebras. I'm going to try to define as much as possible in a unified framework. So in this picture, G will be a simple Lie algebra or Lie superalgebra. It will be a BCD type, and it could be an odd type. So it's either going to be a BCD type Lie algebra or some OSP, and this N can be even or odd. Okay. And just like before, this Lie algebra is going to have a decomposition where it's a sum of 2 Lie subalgebras or subsuperalgebras and some modules for the sum of those. Okay, so this plays the role of the SLN and the GLM that I had before. It's just that they now have different types. So A and B are Lie subsuperalgebras of G. A, there's only 2 possibilities. It's either SO2n plus 1 or SP2n. So A is always a Lie algebra. It's always a B or a C type. Okay. And then B can be anything, any of these types. Okay, and then these modules will be, this is, when I say the module is rho A tensor rho B, rho A is the standard representation of A and rho B is the standard representation of B. Okay, so there's only one tensor product of 2 simple modules here. In some way that makes this problem easier than the type A problem. Okay, and these modules can be even or odd depending on the where they come from in this Lie superalgebra G. So if G is a Lie algebra, then of course they're even. If G is an OSP type, sometimes they're even and sometimes they're odd. Okay. Now let's say that as before, I want to define a nilpotent in the corresponding W algebra of G. I want to define a nilpotent, define a W algebra of G. So this nilpotent, I'm going to denote it by F sub A. It's going to be the one which is principal in A and trivial in big, just like before. So this A is the subscript tells you which one is principal in. And W psi of G F A. I'm going to change notation from my notation before for convenience. So this psi is now a twisted level. So the level of this object is not psi, it's psi minus H check. Okay, it's a little change of notation before, but I think it's more convenient. Okay, so this is true in all my examples. And now let dA be the dimension of row A. That's the standard representation of A. And dB is the dimension of row B. Okay, I'm going to divide all my cases into 4 cases of case 1 and 4 of case 2, where the first division of cases has to do with whether the subalgebra A, which is the one where the nilpotent is principal, is that, remember, that can only be B type or C type. Those are going to be my, when I'm in case 1 and case 2. So case 1, this A is going to be B type. Okay, and then the dimension is 2m plus 1. Case 2, A is C type, and the dimension is then 2m. Okay, and in both of these cases, the corresponding W algebra is going to have this structure. So it's quite reminiscent of the structure that we had in, for the hook type W algebras of type A, where in weight 1, I have dimension of B fields, and that's because the affine subalgebra is of type B. Okay, for some level psi prime, which I'll tell you in a second in each of the cases that we need. So in weight 1, I have generators for an affine algebra of the We superalgebra B. In weights 2, 4, up to 2m, I have an even field, which is invariant under B. And then in this other weight, dA plus 1 over 2. So it depends on the dimension of the standard representation of A. I have dB fields, and those dB fields are exactly the standard representation of B. So I don't have the standard plus its conjugate, I just have the standard. That's a way in which this differs from the type A picture. So all these W algebras have the same shape, and these fields can be even or odd. The parity is the same as the parity of row A tensor row B. Does that make sense? So this is what the general structure is. Now I have to tell you what it looks like in the cases we need. So unfortunately, I can't remember all these cases. I think it's impossible to remember all these, but maybe we'll have to go back and refer to it later if necessary. But the way I want to organize this is by, first I'll do all the case ones, which are when A is type B algebra. Okay, so G is varying, B is varying, but A is type B. That's how I'm in case 1. 1B means that this algebra B, which is the one that corresponds to the affine subalgebra, is type B. Okay, so this W algebra is W psi of G, in this case is a type D. This F is the nilpotent, which is principal in SO2n plus 1. And then I want to take affine coset by this B algebra. And the shifted level here is xi minus 2n. Sorry, it's a phi, I keep calling it a xi. Okay, that's what my affine coset is. And in this case, I have to take a Z2 orbifold because it's really not the SO2 n plus 1 invariance that I want, it's the O2 n plus 1 invariance. So I have to do this extra orbifold. Okay, that's case 1B. And they're all defined sort of similarly, but these algebras have very different behavior. So here my G is an OSP type. My A again is a type B. That's what it means for case 1. And the subalgebra B is an SP. That's why it's 1C. And here I take just the affine coset. I don't need to take an orbifold. Okay, so 1D, well, B should be type D. A is still type B. This is, again, the G is a type B Lie algebra. And then 1O, O refers to the fact that B is an OSP type. A is the same as before, it's a B type. Here I've shifted it to 2m minus 1 just for notational convenience. But I can think of this, but this should be called 1O because B is type O and A is type 1. Okay, so this is my list of affine cosets here. And so these two also get a Z2 orbifold. And my notation, you don't see very much information in my notation. This is to simplify when I write down at the end the trialities. So I write down the affine coset with my 1b, 1c, 1d, and 1o notation. I leave out all this stuff. That all make sense? Okay. And then similarly, I have the type 2 cases. So the type 2 cases, my A, this is the Lie subalgebra where the nilpotent is principal, is always an SP type. It's always type C. And then the B algebra is varying. So the first one is the B algebra is type B. Here the B algebra is type C. Here it's type D. Here it's type O. And again, I always have to take a Z2 orbifold unless my affine subalgebra is an SP, then I don't have to do that. But in all other cases, I really want to take the orbifold under the orthogonal group or the orthogonal supergroup, not just the SO or SOSP group. Okay, and I have similar cases that are denoted in this way. Okay, so this is a list of all my cases, and I've written down, there's a lot of stuff in this notation. I've written down what the level is for the affine algebra, and I've made some notation for these affine cosets. Okay, so unfortunately, it's not possible to state the triality in one slide because there are 4 different trialities that should be thought of as fairly independent of each other. So there's certain isomorphisms between 3 of these algebras, but they mix types. There's no statement for just type B, type C, or type D, but they mix types. And they don't belong together. There are 4 separate ones. I'll say a little bit about what I mean by that later. And so I have to state these things now. What I want to do is state the results and then like indicate some cases where they extend results that we already know. And I also, at the same time, want to mention what some extremal cases are. So I haven't mentioned extremal cases yet. These work for a certain range, but when when M is 0, M is the one that refers to the part where it should be principal, then I have to define these things differently, just like I did in type A. So I'm going to mention that as we need it. Okay, so the first family of trialities I'm going to call 2B, 2B, 2O. So what this means is that one triality is between 2 different 2B algebras where the rule of M and N switches. And then another one is going to be between a 2B and a 2O algebra. So here's I find it convenient to write them as separate statements. So the statement is that for all N and M, the 2B algebra, NM is isomorphic to a 2B algebra where M and N switch, and there's this change of level. Okay, so what was 2B? Well, that means that the algebra where the nilpotent was principal was an SP. The affine coset part the affine subvia way is a type B, and this is inside some OSP algebra. So this is the definition of it. If you forget, I already forget it too. So first thing I want to mention is that the case of M equals 0, I have to define this slightly differently because this is one of my extremal cases. So when M is 0, instead of taking a Hamiltonian reduction, what I do is I take my SO2n plus 1 affine algebra, and then I tensor it with a free fermion algebra of rank 2n plus 1, which has an action of the level 1 SO2n plus 1 algebra, and then I take the diagonal coset. Right, so this L1 SO2n plus 1 acts on this second factor, and I can consider the diagonal coset. That should be my definition of C2B n comma 0. And when I say under this triality, or this is just a duality, this is isomorphic to a C2B 0n, that is just a principal W algebra of OSP 1, 2n with a Z2 orbifold. So this gives us a coset realization of this orbifold of the principal W algebra. So this is like our coset realizations of W algebras before, but it's sort of a new statement of this kind. Okay, so that was 2B, 2B. And now there's also 2B and O. And I have to do this slightly differently depending on whether N is bigger than M or less than M. Okay, there's a little bit different formula for this shift. But this is what the trialities look like in these cases. Okay, so it turns out that all of remember that these algebras are realized from I'll come back to this point later, but I'll just mention this now as a motivation for why I think of these trialities as belonging together. These are going to come as one parameter quotients of some universal algebra. they will correspond to certain families of ideals in the parameter space. The ideals have a uniform description in terms of n and m in this triality family. And for the other triality families, there's a different description. And you don't get the same list of ideals. But this is the same list of ideals for all the 2B and 2O algebras. Okay, so that's the first triality. The next one I'm going to call 1C, 1C, 2C. So this is a similar statement that there's a 1C isomorphic to a different 1C where the role of n and m switch. Okay, remember that n and m play very different roles. One of them is the affine subalgebra, one of them is the piece where the nilpotent was principal. So these are very different structures. It's not obvious that you should have such a triality. And again, in the case m equals 0, this gives us a known statement. So when m equals 0, first of all, I have to define this differently. It's going to be the W algebra will, well, this actually is not one where I have to define it differently. It's simply an affine algebra. So the W algebra when m equals 0 is simply a affine algebra of OSP 1, 2n. And this coset is a coset of the even part, the SP2n part inside OSP 1, 2n. So the other side of this triality is that this is isomorphic to a principal W algebra of SO2n plus 1. So this is a coset realization. In this case, it's of a B-type principal W algebra, but then that's isomorphic to a C-type principal W algebra. So we get a coset realization of B and C-type principal W algebras. And this was also proven in a different way by Kreutzig and Genra, using a method that's more like the original proof of coset realizations in the ADE setting. Okay, so this is another way of getting this result. That was the 1C, 1C duality, and this is a special case of it. There's also a 2C, 1C duality, which I won't say anything more about. But these also play a quite different role because 2C, the Lie algebra G, this is the 2C W algebra is of an SP type Lie algebra. The 1C is of an OSP. So these are very different structures, and we get such a triality. Okay, that's the second one. So now here's the third one, 1D, 2D, and 1O. So I'll first mention 1D and 2D. Again, the affine algebra is in both cases type D, but one of these is 1D. This is a W algebra of Lie algebra. 2D, it's an OSP algebra. And when n equals 0, you have to go back to the definition. It's probably not obvious just staring at this, but one of these is W psi of SO2n plus 1. It's a B-type principal W algebra. And then the other one is a C-type principal W algebra. Here, there's no orbifold. So this statement in the special case n equals 0 recovers Fig and Frankel duality in BC type. When n equals 1, it recovers a duality that I'm going to call Kreutzig-Genra-Nakatsuka duality. It's between Heisenberg coset of certain subregular W algebras type B. So this was also proven in a different way using free field realization. That is the case n equals 1 of this general statement. And that was 1D, 2D. There's also a 2D, 1O isomorphism. Okay? And I want to say one more thing about this. So this 2D, 1O isomorphism, it doesn't matter whether n or m is bigger. This statement holds in all cases. But if you look at the first statement here, the 1D, 2D, notice that for the 2D algebra, the second coordinate, this m plus n, is always bigger than n. Okay? So the 2D algebra, when the second coordinate is bigger, is actually part of a different triality than the 2D algebra when the second coordinate is smaller. So it's a little strange that these three things belong in one family. The ideals all can be described in a uniform way. But my last triality, I also see 1O and 2D, but this 1O and this 2D I have to think of as different because the size of, relative size of m and n is different. Okay, so here I've got, first of all, 1B and 1O duality. Again, this is a special case of something I know. When n equals 0, the 1B with n equals 0 is the principal W algebra of type D, SO2n plus 2 with an orbifold. And when the 1O object is a similar thing, except that I have this level psi prime. And this is exactly Fagan-Frankel duality in type D, except that I'm only comparing the Z2 orbifold piece. It's the Z2 invariant part of Fagan-Frankel duality in type D. The other duality, this 2D10, in this case, recovers the Z2 invariant part of the coset realization of W-algebras of type D. So I didn't write down the details of this, but if you go back and look, you see that it's exactly the same statement. As I said before, notice that, let me just go back to this slide. So as I mentioned here, which 2D algebra is appearing? The second coordinate is bigger. So if you go back to the 1O algebras that appear in this duality, that means that the first coordinate is bigger, right? Because they switch roles. So on this slide, which 1O algebras appear? Well, second coordinate is bigger. So they're not actually the same. So there's no way that I can combine 1B, 1O, 2D triality into this triality, 1D, 2D, 1O. They have to be thought of separately. So I actually do get 4 separate families. Okay, so that's all the statements. And this looks like a huge mess, but it turns out that the way that one can prove this is very uniform. And the proof is very similar to the type A case in the sense that I use a universal object, but now it's the universal even spin W infinity algebra. So this is something which was also mentioned in much earlier physics papers, but not like a clear conjecture. I think the first time I'm aware that it was clearly conjectured to exist in physics is in 2013. So this is a universal algebra, which also has 2 parameters. It also has, I'll call them C and lambda. This lambda is different from the other one, but C is still the central charge. The generating type is 2, 4, 6, 8, all the way out, has infinitely many generators. So it's generated by a Virasoro field and a weight 4 primary field. It's freely generated of this type. So again, it has PBW basis. And it's also a classifying object for VOAs of this kind, where you have things in even weights up to some point. So all VOAs of this kind satisfying some mild hypotheses arise as quotients. And that includes many well-known objects like B and C type principal W algebras, and also the Z2 orbifold of the D type principal W algebra, but also many others. So the existence and uniqueness of this algebra was constructed in my paper with Shashank recently, last year. Similar story that one can talk about its 1 parameter quotient. So you can look at ideals in the parameter space. Take the corresponding VOA ideal that it generates. So if I is some ideal in this parameter space, it generates a VOA ideal. I can take the quotient to get a VOA over the quotient ring, which has the same graded character, but it may not be simple anymore. For certain nice ideals, this fails to be simple. I can take its simple graded quotient, and I'll denote this with this lower I. And this is now a 1 parameter VOA. And many interesting, it's the same story as before. There are many interesting VOAs that arise this way for some I. There's a question of, can we classify all such I's? And again, and of course, that's still an open question, but the ones that one expects are all on our list. So we find many such examples. And this, I'm going to use, notate, I'm going to say V of I is the variety, or the curve that is in the parameter space C2 cut out by this ideal I. It's useful to have this, well, I'll say a little bit later why it's useful to have this language. I'll call this the truncation curve. You can think of these VOAs as being defined along these truncation curves, the 1 parameter quotients. Okay, so you have 1 parameter quotients. The main idea, just like the type A, is to identify all my affine cosets. We have 8 cases. We have to identify each of them with a 1 parameter quotient of this even spin algebra. And I mentioned before that when V is either a B or a D or a super B or D algebra, in this case it's only an OSP 121, then I have to also take a Z2 orbifold. If I don't take a Z2 orbifold, then this structure is too big, and the affine coset is not a W infinity quotient. So just like before, it's possible using classical invariant theory to show that these cosets are of type W24 up to something. This n is determined explicitly by invariant theory. I do this by passing to some limit where it's easier to see, and then I use general results that persists for the family. So I get the generating type. That means that I can identify these with 1 parameter quotients for some ideal. I want to determine this ideal. So I can think of the big W algebra as a VOA extension of an affine algebra. That's just the affine sub-VOA tensored with this W infinity quotient. The extension is generated by these fields of a particular weight, which transform in a particular way under this Lie algebra B. That's the affine sub-VOA has type B. And the parity is also determined by all this data. So the data is that I know how many fields, I know what weight, and I know what parity. And it turns out the existence of such an extension uniquely determines this ideal I. The calculation is similar, but it's much more complicated in this case. And the formula for these ideals is more complicated. It takes more than one of these pages to even write down the parametrization of the ideal. So in order to work with these, I need to use a computer, but it's not so complicated, the computer can't handle it easily. So I get the description of these ideals, and then all the trialities that I wrote down follow immediately from symmetries. If I do the parameter changes that are required by the triality statements, I get exactly the same ideal. And within those families, the ideals cycle back and forth. All those families, I get the same list of ideals. And I believe that those four families, well, I don't think there are any more dualities than the ones that we wrote down, but I guess I haven't proven that. Anyway, so just a few concluding remarks. In type A, there was one family of trialities that one could write down, and that's because all the ideals you can write down as a single n times n family. So there's an ideal I sub nm. For every pair of positive integers nm, I get an ideal. They all can be defined uniformly using one formula, depending on n and m. That's why there was one family of trialities. And as I mentioned before, we expect that these ideals are all the ideals along which this universal algebra degenerates. So these should be all the one-parameter quotients, but that's not known yet. In types B, C, D, and O, this O is really like super B or D. There are four families of trialities, which I mentioned. They correspond to four distinct families of ideals. And I also think that these account for all of the one-parameter quotients of the even spin algebra. But again, we can't prove that right now. Okay, so this is the end of it. I wanted to leave a few minutes in case there's some questions, but also just say a few words of what one might do next. So these statements classifying all the quotients of these W infinity algebras is for me very interesting, but I don't really know what to do with that problem. All the trialities, another thing that I think is very important is to give a different proof of these trialities using free field realizations. So in some cases, this has been done by Kreutzig, Genra, Nakatsuka, but it's probably possible to find free field realizations of all of these algebras and give free field realizations of the cosets and prove these trialities as well. There are various reasons why it's better, why that proof, there are more things one can do with it, there are different things one can do with it. But it's important to have this argument because also the free field realizations of these algebras have geometric significance. Another thing that is important is to find trialities that go beyond the hook type algebras. So all the ones that we've considered in this talk are so-called hook type algebras. The reason why it's possible to deal with them, first of all, is that the structure of the Lie algebra, the fact that it decomposes as this A plus B plus a nice module, makes it possible to use invariant theory to determine the generating type. Invariant theory is typically very difficult unless you are working with the standard representation of a classical group or maybe the adjoint representation. It's very hard to use invariant theory. And the other thing is that we have these unifying objects, these W infinity algebras in those cases. But if one were to go beyond the setting of hook type W algebras, there should certainly be a much richer family of trialities, but it'll be more difficult to prove. So another reason to develop other methods of proof is so that we can handle more general problems. And then of course, if you want to develop this approach, it's also interesting to construct more general unifying objects, things like these W infinity algebras, but maybe depending on more parameters and maybe with more complicated generating types. So in some cases, I have ideas how to do that. In many cases, I have no ideas. So that is all I wanted to say. So maybe, I think there's a few minutes left in case there's some questions.
Thank you, Andy. Are there any questions? Just go ahead and unmute yourself if you have a question. Yeah. Oh, Naoki? Yeah, go for it, Naoki.
I think you're still muted.
Okay.
Now,
Yeah, very, very interesting talk. Thank you, Andy. I really want to ask, your statement includes the coset using these orbifold.
Yeah.
In BCD type, but I guess some cases also hold if you omit these orbifolds. I mean, if you consider coset itself also satisfying the other coset.
Yeah, I'm not sure. It's probably true, but I think so. Yeah, I think that's right in those cases. Yeah, the ones that unify, yeah, I think so, because, yeah.
How do you think? For example, in our case, we don't need to take these
That's right, yeah, BC type, you don't need it. Yeah, OSP, you do need it. For the coset realization of the principal OSP, you have to take orbifold in this setting.
So why you need to use taking these orbifold?
That's so that I get a W infinity quotient. So yeah, so these objects they make sense. So you do get, well, the only thing that I have proven is that the Z2 orbifolds are isomorphic with this picture, because the Z2 orbifolds I identify with W infinity quotients, and then there's a method for determining which W infinity quotient. So yeah, the argument that I presented only works for the Z2 orbifolds, but the statement probably can be extended.
Okay, thank you.
Any other questions?
I have one question.
Yeah.
So in the case of A-type, W infinite algebra has a meaning of the chiral of all the differential operators that I remember. Do you have some picture for the even spin W infinite algebra? I think it's a kind of OPA theory or something.
I don't know exactly. I don't think it's so easy to extend this picture directly to this even spin algebra. So maybe there's a way to do it, but I'm not sure. There is some physics paper by Prochaska that gives a picture for this. There also, and one of the statements in his paper is that you can realize this even spin algebra as a subalgebra, not of the type A one, but you have to tensor it with a Heisenberg. So if you take W infinity of type A, but you throw in one Heisenberg, then you can realize the even spin algebra is sitting inside that. It's not an orbifold, it's something more subtle, but it does live inside. But it's not exactly the type A picture.
Okay.
Okay, if there are no further questions, let's thank Andy again for the Zoom clap or an actual clap, whatever you want.
Thanks very much for listening.
Thank you very much. And I hope you'll join us again for Jingwei's talk on September 24 using the same link.
Okay, very cool.
Okay, thank you so much, everyone. Thank you, Andy. See you soon.
Bye-bye.